Hello, here's lesson 10b. So this is one that's also about linear growth and exponential growth. So the last lesson we looked at really looked at the rabbits and how they grew. And in this example, we're actually going to look at population data. So a little bit different and perhaps a little bit more meaningful here. So question one, they're saying, how do we get our information? So which sources are the reliable ones? So I would say probably for this one, I might go with the Census Bureau, right, to actually get reliable data. So they collect data often, so we can trust that their numbers are pretty close. Anything that uses a lot of estimation, we would call into question some of the methods. But anyone that collects data often and updates it, then we can be pretty happy there that that data is pretty accurate. So let's look at what we're going to do for the rest of the lesson now. So we're going to look at the world population data. And we'll take a look at this question 2 here. So normally we would do this in groups. So I'm going to pull the data that we had from the preview lesson, right? It looked like this here. So this is data from 1950 all the way to 2010. We could most likely soon get the 2020 data. And so you can see the change in the population here, right? This is how the population has grown. We are over 7 billion now. And here we have the differences, right? So we simply take the previous two numbers here and we subtract them, and then we get the difference in this column, right? So this is showing us the first difference, the actual growth. And then here we have the growth rate, where we take the recent data and subtract the old and then divide it by the old. So we've seen this in a few different activities in this class. So it's saying here, determine if we can tell by looking at this data, is it linear growth or would it be more of an exponential model? And of course, how do we know the answer to that question? So when you look at this, you can actually answer both of those questions. So if we were to examine this column here, here we're looking at adjacent numbers and we're subtracting them. So if this model were actually linear growth, then what we would expect to see in this column is all the exact same numbers, right? And this would be related to what we call the slope of the line. But you can see there is definitely some significant variation here. In fact, these two numbers here vary by practically 100,000, or I should say 100 million. So there's a huge variation here when we look at these. So because these numbers are not constant, they're not the same, this is definitely not linear growth. Now what we have in this last column is the average rate of growth, right? So this is where we take, again, the new data minus the old and then divide by the old. Now if you look at, for example, the first 4 entries, we can say that these are pretty close to being constant, right? So all of these are in the vicinity of around this number, right? 0.20. You can see about 0.19 here, 0.22, 0.19 again, and something pretty close to 0.19, right? So if this last column is about constant, this is suggestive of exponential growth. So what we can say to answer this question, right, we're not seeing this be perfectly constant because it kind of it tapers off a little bit here, right? It drops a little bit, and that's because of these numbers here, right, are getting closer. So I think that answers that question, right? We can definitely say for the world population growth, it is definitely not linear. It's almost exponential, right? So it's exponential at a certain time, but then due to lack of resources and overcrowdedness, we start to see this change a little bit. Okay, so I believe page 2 here is where we have most of the math that we're going to see in this lesson. And I think question 3, we pretty much have it answered here if we look at this table. So again, it's saying examine the values of the average rate of growth. So that's this last column here in the preview. And it says, if the data represent an exponential relationship, what should you see? So we've discussed this, that this should be about constant. And then they say here, why do you not really see this to be exactly constant? I think a quick way we can answer this is when we talk about an exponential model, it's really a theoretical model. And so what we're seeing here in real life is oftentimes you don't get something exactly theoretical, right? So you're going to have something that's pretty close to what we would call an exponential model, but it's a little bit different than what you would see in a textbook, right? So a perfect textbook example, you might see no change in these numbers, right? They're all exactly the same, but in real life, you're going to see slight variations. And this is due to things like just variations in the growth rate, disease, right? Different things like that that play in. Okay, let's go to number 4. This is an algebraic problem. So what we're looking at here, this is the r divided by the p, right? So this is the first difference actual growth, and then it's divided by the p, which is the actual population. So they tell us here, solve the equation for r. So I'll go through it and do that. So I'll write this out first. So this is what it looks like. So if you want to, you can drop the multiplication symbol and just not write anything at all. So to solve this equation, right, for r, we can multiply both sides by p, just like that. And then we get the two p's here will divide out. And that's pretty much it, right? So r here is going to equal this expression. So there's a bunch of ways that you can write that down. That's a nice way to just leave it. And so with this, what we're going to do is we're going to fill in the table in number 5, and we're going to fill it in with what we just solved for. This is r, which is the rate. So I'm going to put the right-hand side of this right here. And so we're just going to remember here, this is the actual growth. Right, the actual growth rate. And then they say for different values, when p is equal to 0, let's calculate this. And they give you this information here. So I'll show the details for one of these, and then we can kind of fill in the rest. So k is equal to 1/10, right, 0.1. L is equal to 100. And what we're going to do is to keep calculating this, right? And then we'll put the value in this column. So let's do one of them. So r is equal to k, which is 0.1, and then L minus P. So L is equal to 100. So L minus P, and P for this first one is 0. And then lastly, multiply by P. So this is what we get to calculate in this first cell. We have a 0 in here, so anything times 0 is going to equal 0. And then for the rest of the table, you still use this K and this L, but you keep changing the P, right? So you do it for different values of P, and then you can fill in the table. So you can try this on your calculator. So you see the numbers definitely go up, and then what happens is they drop, right? So there's a reason why this happens. This one should make sense. When P is equal to 100, right? If L is equal to 100, then right here you have 100 minus 100. So your center entry is 0, and that's why we get this 0 here. So we filled in the table, and then it says also to sketch a graph, right? So to really show what does this look like as a graph. So I'll go over here and do it. I'll do just a rough one. So P is acting like our x, right? So this is our x coordinate, and then R is our rate. So the entries for P, right, jump up by 25. So I'll do 25, 50, 75, 100, right, something like that. And then the values in this column, the biggest one is 250. So I might do 100, 200, 300, something like that. so we can make sense of that scale. So I'll label 2 of them. That's 50. And then maybe this is 200. Right? So if you now plot these points, okay, the first one is 0, 0. So that's going to put us right here. 25 and then 188 or so. So 25 and pretty close to the 200. So right about there. And then the 75, you're going to see the same value. So I'm going to jump to that one. At 50, you're going to be all the way up to 250. So I'll put that point there. And then at 100, you're going to be back to 0. So this sort of makes sense if you look at the shape. This might remind you in algebra a little bit of a parabola, right? So as the population goes up, what happens to the rate, right? The rate of growth goes up, but then at some point when the population gets too big, the rate of growth starts to drop, right? And this is something that should make sense if we actually think about it. And we'll see that in the last 2 questions, number 6 and number 7. So speaking of, let's take a look at number 6. So this is saying, assuming the stuff we did above, right, number 4 and 5 is right, let's think about the answers to these questions. So what can we say about the population growth when the population is very small, right, close to 0? So you can look either at the table or the graph. I really like graphs because they kind of help us think. So when the population is very, very small, you can see the rate of growth is also very, very small. The reason for that is if the population is tiny, there's little room to grow, right? There aren't that many opportunities to breed, and the population is slow to sort of rebound, right, to start to grow. Now let's look at part B. It says, what can you say about population growth when the population is very close to L, right? Remember the value of L is 100. So they're saying when the population is close to 100, so that's right about here, right? They're saying, what can you say about the rate? Well, the rate here is also very, very small. And the reason for this, though, is different than in part A. So in part A, if the population is small, we have reason to think it's going to be slow to grow. But here, the population is very, very big. So the reason the growth rate is now small or slower is because perhaps of limited resources, limited room, maybe overcrowdedness, right? So both of these examples, both part A and part B, we're seeing a rate that's pretty small, but for very different reasons. And then finally, question C. What can we say about the population growth when the population is very close to the middle of the graph, right? So this is referring to this part of the graph, right? So when the population is sort of in the middle, what can we say about the rate? The rate is at its highest, right? So what we're seeing here is the population is going up. Perhaps the population is large enough to allow for lots of breeding, but it's not so large as to cause any problems with resources, things like food and also space, right? So here is where we, part C is where we really see the maximum growth rate. All right, and then let's finish off with question 7. This is a nice question where we can look back at number 4 and 5 and then think about what a graph would really look like. So let's take a look at some of these. Here it says start with a small population at a given time. How will the population change, right? So this we kind of already touched on, that if the population is small, the growth rate will be pretty small. But at the same time, as the population increases, so does the growth rate. So we kind of think of it this way, right? If the population increases, what happens with that? The growth rate is also going to increase, and that has a snowball effect. So as the growth rate increases, this population is going to increase. As the population increases, the growth rate increases as well. So in one of the earlier lessons, we saw this sort of compound growth with with money sitting in an account. So this is the same basic idea. But then at some point, you're going to hit a wall where this population is going to be so big that it can no longer sustain itself. So then this growth rate, even though it's increasing, it's now going to start to drop, right? It's going to get smaller. So question B, now that it's grown significantly, how will the population change? So I was alluding to this, that the population still grows, but the rate is going to slow down. So I'll jot that down. So the rate eventually slows. And then they say, look back at the equation, right? What is it about the equation that we talked about that causes this behavior in the growth rate? So why does the growth rate slow down and drop? So what we had there, it was this one here, where we were told to solve for r. So this is the equation that we had there. And so they told us to use 1/10 for k and 100 for L. So that's what the equation looked like. So now it's interesting here because you can see as the population increases, right, you'll notice that one part of this equation, so I'll highlight it right here. Right, so as the population increases, the 100 minus p has a different effect, right? That's going to decrease. So as p gets closer and closer to 100, this thing here is getting closer and closer to 0. And what that's doing is that is affecting the rate. So even though the rate is still positive, it starts to drop. So I think now we have enough information to answer part D. This is kind of the big part of this. It says, try to create a rough sketch of what the population size looks like over time. So again, I'm going to just flash this up here really fast, right? That as the population gets bigger and bigger, you can tell that the rate soars, right? And then the rate hits a maximum point. But then as the population gets bigger and bigger, then the rate starts to drop, right? So we're seeing that kind of impact where the rate is the greatest right about at the middle. So what is that going to look like if you actually try to graph this? So I'm going to make an attempt here. And this will just be like a freehand graph, right? We're not going to be super precise here. But I would say we have time as your independent variable, population as your dependent variable. And so your graph, you're going to have some kind of threshold here, because we keep on talking about how the population can't be infinite. So eventually they run out of resources, or they run out of things like food. So the population can't really go beyond this line. So the population is going to start like this, beginning of time. We're going to see very, very slow growth, right? So it's going to look sort of like this. But then at some point, the population is going to soar, and it's going to start to look exponential, just like this. So this graph looks a lot like some of the COVID-19 graphs that we've seen, where this is time and this is the number of people infected. But what's going to happen here with the population is as time goes by and the population gets too big, this is no longer going to start to soar, it's going to level off. So it's going to look something like this, right? So the population there is going to run out of some of those resources. So this agrees with what we did in number 5. I'll go back to that in a minute. So if you look at this part of the graph, this is really slow growth, right? It almost looks horizontal, and you see the repeat of that right here. This is slow growth as well, because this is where the population is getting pretty big. This is where you see maximal growth. Right, so you can see the maximal growth right about in the center of the graph. So remember, this is time versus population. So the nice thing to do now, before we wrap up this video, is to look at this graph and to see how it kind of gives you the same information as this one. As the population gets very, very big, the rate fluctuates, right? The rate starts very, very small and slow. The rate is still small here, but it hits its maximum point right about in the center, and you can see that the graph here is at its steepest right about in the middle of the graph. All right, that's it for 10b.